reflected here in miniature, a part of the story of our future, and expanded around the world, a network of space-age instruments to record the future as it becomes the present. Today, a vast electronic communication system called SpaceTrack senses and plots the course of all in-space man-made objects. Although the United States possessed the technical know-how shortly after World War II, it was the Russians who placed the first satellite in space. As of midsummer 1961, the Soviet Union had placed 15 devices in orbit, with a total announced payload of 109,000 pounds. The United States total, 51 devices in orbit, with a cumulative payload of 30,000 pounds, plus 29,000 pounds of engines and tanks. The steady activity of SpaceTrack's computers tells the story clearly. We have entered the space age. Throughout human history, the phases of man's evolutionary development were symbolized according to the implements men made, and we employ the words space age as we would Stone Age or Iron Age, although these were eras which ran virtually changeless for centuries. But now we are in a period of accelerating change, as one age merges into another, as new ages are born before the previous one has matured. The past 100 years of man's time on Earth have been named by some the technological age. We have lived in the air age during the second half of this technological age, and in the past quarter century, the electronics age, followed quickly by the jet age, the atomic age, the age of missiles, and now we have broken through into the space age. But though these ages have come in rapid succession, one after another, there has been no defined separation. All of the ages have been fused, blended, one leaning on, learning from, and leading to the next. The result? A technological explosion, propelling us into the space age and building up new forces which may make unprecedented changes in the daily lives of all mankind. Though the space age is new, our base for space, our many facilities, our know-how, our most priceless asset, trained people, have had a long history of development. Today's satellite systems are providing us with a new line of sight from record altitudes, just as we achieved a major extension of our sight prior to World War I with the first airplane purchased by the Army Signal Corps. There were pioneers who extended our air age knowledge, too. The Wright brothers, Billy Mitchell, Lindbergh, Jimmy Doolittle. Wright-Patterson Air Force Base, Ohio, is the home today of an Air Force division devoted to research and analysis of foreign technologies, with particular emphasis on space. It is also the site for investigations of man's ability to adapt to the space environment. But it should be recalled that the first such facility at this location was established in 1918. It was early recognized that man's own limitations were an effective barrier against the full exploitation of flight. High-altitude chambers were created to simulate flight environmental conditions, and pressure suits for protection against extreme changes in environment. Today's research, dealing with the more drastic environmental changes in space, quite logically utilizes the knowledge gained in the pioneering air age investigations. A typical problem to be faced in space is weightlessness. This unnatural environment has been partially simulated during prolonged periods in a minus gravity condition. Also, by flying a special maneuver, the state of zero gravity has been accomplished for brief periods. But before you can place man into space, you must have developed the means of transporting him there. In 1954, few realized that we were starting to build the springboard into the space age when the Air Force established its Western Development Division in a former schoolhouse in Inglewood, California. A small nucleus of hand-picked R&D officers and experienced scientist engineers soon expanded to become the Air Force Ballistic Missile Division. To achieve the goal of developing ballistic missiles at the earliest possible date, new resources, scientific and engineering talent, military skills, and industrial initiative were mobilized to a degree never previously experienced in any single program. There was a mountain of work to be done, and it was done. Today, we survey the results of 7 years of concentrated effort to develop unprecedented management concepts and capabilities. 7 years distinguished by the achievement of many major milestones. On September 9, 1959, an Atlas intercontinental ballistic missile with a specification range of 5,500 miles was launched operationally by crewmen of the Strategic Air Command. The flight path of another Atlas blazed a trail from Cape Canaveral to the Indian Ocean, east of Africa, more than 9,000 statute miles. However, intercontinental range missiles did not spring full-grown and problem-free from the drawing boards. One of the most challenging problems was the question of how to bring the re-entry vehicle back through the atmosphere. The question of re-entry was resolved, but not without a determined, concentrated effort, which paid off in 2 solutions. One, the ablation solution, used in military missile nose cones, and the heat sink solution, applied to the Mercury man in space capsule. Early in the Atlas flight test program, it became apparent that confidence in the Atlas was justified. In 14 flights at the Atlantic Missile Range, 10 re-entry vehicles fell within 1 nautical mile, and an 11th within 2 nautical miles of the target. And now, across the American continent, Atlas squadrons take their place in our first line of defense. At some of these sites, the Atlas will be in hardened horizontal launchers. At others, in underground silos designed to withstand nuclear attack. Our second ICBM, Titan, gains a weight advantage over Atlas since its lower stage is dropped on reaching altitude. Thus, it can carry a heavier payload greater distances. A follow-on version, Titan II, will use storable fuels and be launched directly from an underground silo, as was this specially modified test missile. Titan II can be launched within seconds following the fire order. Titan strategic missile squadrons, with their underground silos, crew quarters, and launch control centers, are being activated across the country. The Minuteman ICBM introduced a new concept, a solid propellant ballistic missile. In a series of tests, only 8 of a scheduled 18 launches were needed to confirm that the Minuteman firing from the hole concept was feasible. In February 1961, the first full-scale Minuteman was ready. All 3 stages separated as programmed in this unprecedentedly successful first launch. By early 1962, 16 squadrons were funded, representing 800 missiles out of a planned total of 1,200. An essential ballistic missile in today's inventory is the intermediate-range Thor. Thor was even more significant as a challenge to the evolving R&D management team concept. The first of the long-range missiles to achieve operational status, Thor proof-tested every aspect of the new system's management capability. Immediately after contracts were signed in December 1955, fabrication and testing began. As is the case with any new weapon system, testing had to be thorough and complete. Many and varied tests of the missile prior to that final test, flight. Just as with Atlas, Titan, and Minuteman, primary flight testing of the Thor took place at the Atlantic Missile Range facility, Cape Canaveral. Here, a little over a decade ago, palmettos and sand made up the landscape, a scene which has been converted through the years into a series of some 40 different launching pads, with their gantry cranes, instrumentation and support buildings, antennas, and guidance and control equipment. Downrange, too, facilities were created, stretching southeast more than 5,000 miles from the Cape to Ascension Island, a network of instrumentation-studded island sites to record missile flights and to listen to and report each function taking place within the missile. The Thor testing program at the Atlantic Missile Range was an extensive one. Here, clearly, the achievements of the electronics age serve those of the missile age. Ocean-going ships and aircraft were later added to the chain for additional tracking capability. Camp Cook, California, was renamed Vandenberg Air Force Base and a West Coast launching and training facility for both IRBMs and ICBMs activated. Here in December of 1958, an Air Force crew launched a Thor missile, and shortly thereafter, in a demonstration of operational readiness, an RAF crew did the same, giving strong support to the program for deployment of Thor to the United Kingdom. By December 1959, just 4 years from program inception, the first Thor squadron was declared operational. This record time stands as a tribute to the management industrial team capability to produce, train and deploy, and to prove booster reliability. The reliability built into Thor and proved out in repeated launchings led to other uses. On October 13, 1958, Thor, with an added second stage, was used to hurl a payload, Pioneer 1, the farthest distance from Earth of any man-made object at that time, over 70,000 miles. At this historic point, the techniques and capabilities of the missile age, utilizing the advanced state-of-the-arts of the electronic age, were beginning to lend themselves to the dawn of a new age, the age of space. While these strides into space were being made, the combined Air Force and industrial facilities base was augmented to meet new space-age demands. A tracking station agreement was made to utilize the Jodrell Banks radio telescope, the world's largest. This 300-ton, 250-foot dish can receive signals from as far as 70 million miles. Other sites were established, including this one at South Point, Hawaii, with a 60-foot antenna having a 20 million mile reception range. South Point and Jodrell Banks, between them, can provide almost 24-hour command and telemetry reception. Shortly after Pioneer 1, the Able 3 program placed Explorer 6 into orbit with an initial 22,000-mile apogee. As the next step, a three-stage vehicle was designed to place into orbit the Pioneer 5 satellite. Pioneer 5 set new records in space communication by sending signals from more than 22 million miles. The Secretary of Defense responded to the growing need for improved centralized management of the space programs under development within the jurisdiction of his department. In September 1959, he delegated to the Air Force the responsibility for developing and launching all military space and satellite boosters. Because the Air Force also supports NASA in its programs, most American ventures into space have utilized the missile launching facilities, the tracking, communications, and technical networks created by the Air Force. Thor Able-Star has been used successfully in the Army's Courier Communications Satellite program and the Navy's Transit Navigation Satellite. In April 1960, Thor boosted into space NASA's first Tyros weather satellite to transmit pictorial weather data. From altitudes of up to 450 miles, the results clearly demonstrated the feasibility of using an Earth satellite to provide usable weather information. Thor has also been used to boost the Agena satellite vehicle in the Air Force's Discoverer program, dedicated to proving out the many capabilities of Agena for application in numerous space programs. The Agena offers many characteristics, making it uniquely suitable as a space vehicle. It can be controlled, directed, reoriented. It can communicate. It can restart in space. All of these capabilities, and more, were to be demonstrated in the Discoverer program. Tracking stations for the polar orbiting satellite were established, like this one at the launching site, Vandenberg Air Force Base, at Kodiak, Alaska, at Kaina Point, Hawaii, and at New Boston, New Hampshire. At Sunnyvale, California, the Satellite Test Center was established as the nation's first military organization whose sole area of operation is space. The Satellite Test Center is an operating activity of the 65 94th Aerospace Test Wing satellite, the Air Force cadre whose operational environment is space. From the satellite control room, the Air Force is able to monitor Discoverer flights from launch through mission completion. The Air Force personnel manning the Sunnyvale controls exemplify the type of blue suit capability being developed and encouraged by Air Force policies which are geared to attracting and retaining highly qualified technical and scientific personnel. This fog-shrouded vehicle, Discoverer 13, was scheduled like the 12 which preceded it for launching from Vandenberg Air Force Base. The date was August 10th, 1960. The tracking stations picking up the signal confirmed orbit, while at the Satellite Test Center, progress of the launch and orbit were carefully monitored. As programmed, a capsule within the Agena was ejected after the satellite completed 17 orbital passes around the Earth. Recovery plans call for an air grab of the capsule, backstopped by an alternate plan should water impact occur, as it did in this case. C-119 aircraft marked the location until recovery was accomplished by helicopter. Recovery of a man-made object from a satellite orbiting the Earth stands in this phase of the technological age as a unique synthesis of air-age, electronic, missile, and space-age skills and techniques. Agena, produced on an assembly line basis, is also serving other major military and scientific efforts. For these programs, the proven Atlas has been called into service as the booster. The same combination has already been used for NASA's Ranger, which is designed to culminate in moon impacts and the sending of scientific information back to the Earth. Agena will also be used for the Army-managed Advent, which will investigate the feasibility of using satellites for microwave radio communications. Another Air Force program utilizing Agena and Atlas boosters is Vela Hotel, a project to gain information for an operational system for high-altitude nuclear detection. In view of the secrecy with which the Soviet Union prepared their 1961 series of atmospheric nuclear tests, the necessity for having a program for detecting nuclear detonations in space becomes crystal clear. The Air Force Midas program uses an Atlas Agena system. The first 2 tests in the series were from the Atlantic Missile Range. A total of 8 are planned from the new Point Arguello space launching facilities at the Pacific Missile Range, adjacent to Vandenberg Air Force Base. The program objective is to provide a system of continuous infrared coverage of the Soviet Union. The Midas payload is designed to pick up any indications of missile launches and transmit the information to a central control and display facility. If an attack is indicated, the information is instantaneously passed on to the appropriate authorities. Midas 3 carried a bonus, or piggyback experiment of high scientific value. HEPDEX, High Energy Proton Detection Experiment. From its vantage point nearly 2,000 miles high, HEPDEX penetrated the full width of the Van Allen radiation belt. It gathered new knowledge on space radiation fields and transmitted it to Earth. HEPDEX has caused recalculations, since it has demonstrated that the Van Allen belt is only 1/2 as large in area of major radiation, but many times as hot as originally believed. For NASA's Mercury manned flight program, the Air Force has the responsibility of providing the modified Atlas booster and its abort sensing system. It is also responsible for determination of trajectories and the launching and control of the vehicles through orbit injection. Both an unmanned Mercury capsule and one with a chimpanzee passenger were successfully orbited in the program before final preparations began for the orbital flight of Lieutenant Colonel John Glenn early in 1962. In this historic milestone, the Air Force once again carried out its Project Mercury assignments by successfully boosting the astronaut into position to complete his planned 3-orbit trip around the Earth. From blastoff to recovery, this first American manned orbital flight has been hailed as the complete success that it is. The solid propellant Blue Scout series of vehicles, now thoroughly tested, are slated for the heaviest program of launches of any of our missiles. Blue Scout stages can be stacked and arranged in various configurations, depending on the payload and mission. The Blue Scout vehicles will be employed for high-altitude experiments, re-entry, boost glide and recovery studies, and for orbital injection of payloads. Blue Scout is assembled, checked out, and launched by the Air Force 6595th Test Wing. These, then, Blue Scout, Atlas, Titan, Minuteman, Thor, and the various space systems, have been some of the concrete, solid accomplishments in 7 years of steady, concentrated work. Though not so easily defined by specific dates, some of the major milestones during the past 7 years involved the development of new scientific, technical, and management capabilities for the nation. From just 2 contractors when the program began, the industrial base has today grown to more than 30 principal contractors, backed up by over 200 subcontractors and a nation-spanning network of suppliers. In recognition of the growth of the missile and space programs and the vital importance that must be continually placed upon effective management to ensure the streamlining of decision-making and other necessary processing, the Air Force reorganized in the summer of 1961 to create 2 new divisions, one for ballistic systems and one for space systems. The Aerospace Corporation is an organization of high technical competence devoted to accelerating the advancement of space sciences and technology. Its immediate objective is to serve the Air Force in the scientific engineering planning and direction of ballistic missile and space programs. In this capacity, the Aerospace Corporation closely supports the missions of the new aerospace divisions through the systems research and engineering phases of R&D program management. Additional human resources, brain power, experience, and skills so vitally needed to meet space-age challenges have been made available through aerospace. The total Air Force family of 10,000 scientists and engineers now represents an impressive capability. In laboratories, work is constantly in progress to provide knowledge of all phases of the technological age. A typical experiment in the many-faceted laboratories employs a fuel cell capable of regenerative use of its fuel supply, a capability holding great promise as a satellite power source. In a shock tunnel, heat transfer rates are studied under simulated conditions up to Mach 23, throwing light on the need for special protective fairings on satellites at altitude. Plasma propulsion studies have shown the possibility of creating a plasma engine, which may well serve as a prototype for spacecraft engines. Low-thrust engines of this and other types would have many potential military applications in space. And ruby laser experiments using a concentrated light beam are showing the way for applications in such fields as space communications, or for pinpointing targets with extreme accuracy, and in mapping planets in far greater detail than has been possible to date. Today's R&D resources are the vitally necessary ingredient to produce tomorrow's space systems. One vital program today is the Satellite Inspector System for Space Defense, which received Department of Defense Development Plan approval in 1960. This program is an effort to develop and demonstrate the feasibility of a co-orbital satellite inspector system capable of rendezvous with and inspection of a hostile satellite. By means of varied types of sensors, the inspector will be able to determine the satellite's intent. Satellite inspection will be a first step in fulfilling the Air Force requirements for inspection, rendezvous, and docking in space. Propulsion research, a key to advanced systems, is continuously underway in both contractor and Air Force facilities. A test firing of this segmented solid propellant motor took place in June of 1961. Engines of this general type have been proposed as the first stage of a Titan III configuration, with a vast potential as a space booster. Even more advanced, an ion engine, which may hold the answer to space travel over interplanetary distances. Such contractor efforts as these are but part of the total picture. The broad base of facilities which contribute important support to the space age headline makers are many, varied, and comprehensive. Industrial resources of this type, with their capabilities for detailed, in-depth research throughout the entire spectrum of space age technology, are becoming increasingly vital to our nation's space effort. Historically, Americans have tended to overestimate what could be done on a short-term basis, and to grossly underestimate what we could do on a long-term basis. Our space age facilities are created for the long-range view and provide a nationwide network of space support bases, each capable of unique contributions to the overall program demands. For example, across the dry lake from Edwards Air Force Base, California, the Space Systems Division operates the free world's largest rocket test facility. Growing to meet the needs of the time, the rocket test facility, which was initiated in 1952, now includes a Minuteman silo test area and a huge stand to be used initially for a NASA F-1 rocket engine with 1.5 million pounds of thrust. Ultimately, this stand will be able to accommodate test rockets of up to 6 million pounds of thrust. Another Air Force space facility is the Special Weapons Center at Albuquerque, New Mexico, which conducts research, development, engineering, and testing in all fields related to nuclear energy. Radiation detection and measurement payloads developed at the center have been carried in both the Blue Scout and Discoverer programs. Located at Alamogordo, south of the Special Weapons Center, is the Air Force Missile Development Center. The Aeromedical Field Laboratory at the center, as primate manager for the Mercury program, trained the now famous astrochimp Ham for his suborbital capsule ride and Enos for his orbital trip around the Earth. Part of the training involved placing the animal in a Mercury couch for a run on the 35,000-foot high-speed track and requiring him to perform simple tasks. The 35,000-foot sled test track serves also to subject missile subsystems and components to the acceleration, deceleration, and vibration forces which would be encountered in actual flight. This kind of test has one obvious advantage over actual flight, since it permits detailed examination of the payload following each run. The Arnold Center, located in Tullahoma, Tennessee, houses various facilities to gain information on missile and space system performance. Rocket test cells can subject rocket engines to functional examination at simulated altitudes of up to 300,000 feet to determine propellant burning characteristics. Such tests early in the ballistic missile programs helped eliminate what otherwise might have been big stumbling blocks to successful accomplishments. The von Karman gas dynamics facilities at Arnold test models at velocities up to Mach 20. Here, the action, slowed down by high-speed cameras to permit analysis, is a model of the Mercury capsule tested under simulated re-entry conditions. Located in upstate New York is still another vital link in the expanding chain of resources for space. The Rome Air Development Center is responsible for developing and testing ground-based electronics equipment for global communications networks and air defense. Another function of this site is development of intelligence devices. Most of these are of the quick reaction capability type, but one long-range development is part of a concerted foreign technology information project, employing computer technology to achieve machine translation of Russian language documents. The Air Force Electronics Systems Division, located at Hanscom Field near Boston, is charged with responsibilities in long-range planning and conceptual design of electronic command and control systems, that most necessary ingredient to link together not only our ground-based facilities, but also those in the air above it, and now provides us with our lifeline to space. The MITRE Corporation provides systems engineering and other technical services to the Electronic Systems Division. MITRE contributes to the accomplishments in blending electronic age hardware with the needs of the space age. Space Track is located in the Hanscom Complex. Here, some of the results achieved by the broad spectrum of space resources can be displayed. But these results are less significant in themselves than for the experience-wrought knowledge, know-how, and facilities that they represent. In the brief period of time since a concerted effort was begun to develop ballistic missiles, we have pushed forward rapidly and far in this age of technology. The space age is with us, and further, in reaching this point, we have developed the physical resources and the human resources, the trained, dependable, experienced people. They have been supplied with the tools to ensure that everything we have witnessed to date is but a prologue. The Air Force assignment in space was augmented in March 1961, when the Secretary of Defense delegated to the Air Force the responsibility for future development of military space systems, including payloads. Just as development of ballistic missiles not only gave us a deterrent power, but also provided us with the springboard into space, so each new success is important not only for itself, but also because it propels us toward even more challenging horizons of accomplishment in the space age. In the few brief years from the beginning of the space age, the Air Force has achieved great progress in developing the resources for this new era. Our objectives in space must now be clearly defined so that they may be met within our resource of time. In order to ensure our peaceful exploration in space, we must include security as one of our goals. Security can be realized only if we continue to achieve the most effective application of our resources, the Air Force resources that are forging military space power.